Prim's algorithm is a classic greedy algorithm used to construct a minimum spanning tree (MST) from a connected, undirected, weighted graph, and it works by gradually expanding a tree one vertex at a time until all vertices are included, ensuring that the resulting subset of edges has the minimum total weight while keeping the structure free of cycles. The algorithm begins from any arbitrary starting vertex, treating it as the initial tree, and repeatedly selects the smallest weight edge that connects a vertex already in the tree to a vertex outside it, by consistently choosing the cheapest available edge that expands the tree rather than forming a cycle. Prim's algorithm guarantees an optimal solution. The fundamental idea rests on two key MST properties. The cut property, which states that for any partition of the graph's vertices into two groups, the minimum weight edge that crosses the partition must be part of at least one MST. And the greedy choice property, which justifies picking the locally optimal edge at each step because such a choice never eliminates the possibility of obtaining a globally optimal tree. Prim's algorithm depends on data structures that efficiently maintain the frontier edges, those connecting the built portion of the tree with the rest of the graph, typically using a priority queue or min heap to select the smallest edge quickly. This makes the algorithm efficient and scalable. In its simplest implementation, where edges are scanned linearly, the running time is O(V²), which is acceptable for dense graphs. However, when a binary heap is used, the runtime improves to O(E log V), and with a Fibonacci heap, it can reach O(E plus V log V), making the algorithm extremely efficient for large graphs. Prim's algorithm not only ensures minimal total edge cost but also guarantees connectivity, meaning every vertex is reachable from any other vertex via the selected set of edges. And because each selected edge links a new vertex to the growing tree, the algorithm naturally avoids cycles without requiring a separate cycle detection mechanism like the one used in Kruskal's algorithm. While both Prim's and Kruskal's algorithms produce MSTs, they differ conceptually. Kruskal's grows a forest by adding globally minimal edges and joining components until only one tree remains, whereas Prim's grows a single tree from one starting point, expanding it outward. As a result, Prim's algorithm tends to perform better on dense graphs where many edges exist, since the priority queue efficiently manages candidate edges, while Kruskal's algorithm often excels on sparse graphs. Because Prim's algorithm requires the graph to be connected in order to produce a full MST. When the graph is disconnected, it effectively yields a minimum spanning forest, computing an MST for each connected component separately. A key advantage of Prim's algorithm is its intuitive progression. At any stage, one can visualize a cloud of vertices included in the MST, and the algorithm ensures the next added edge is the cheapest connection from this cloud to a vertex outside it. This incremental and visualizable nature makes Prim's algorithm widely taught in introductory algorithm courses. Prim's algorithm is widely used in real-world applications that require optimally connecting components while minimizing total cost. For instance, it is used in network design problems, such as laying out electrical grids, fiber optic cables, computer networks, and transportation routes, where minimizing material or construction costs is essential. In computer graphics and geographic information systems, GIS, Prim's algorithm can help construct structures like Euclidean MSTs used in generating meshes, proximity graphs, and navigation networks. In clustering and data analysis, MSTs generated using Prim's algorithm can help identify relationships among data points, partition datasets, or detect community structures by removing high weight edges. In circuit design, MSTs help minimize wiring lengths and reduce latency. Prim's algorithm is also used in robotics, wireless sensor networks, and artificial intelligence contexts where minimal cost spanning structures are required for communication paths, decision trees, or coverage optimization. There are multiple variations and optimizations of Prim's algorithm. For example, the algorithm can be adapted to adjacency list or adjacency matrix representations depending on graph density. And specialized heaps like Fibonacci heaps or pairing heaps can significantly accelerate performance for massive graphs, making it suitable for modern large-scale computational tasks. Additionally, when dealing with geometric graphs, optimized spatial data structures such as Delaunay triangulations can reduce the number of candidate edges, improving efficiency. Despite its simplicity, Prim's algorithm demonstrates the power of greedy strategies in producing globally optimal solutions through locally optimal decisions. Each choice is provably safe due to the cut property. And this makes Prim's algorithm a cornerstone not only in MST computation but also in understanding greedy algorithm design more broadly. Its correctness is typically proven using exchange arguments, which show that whenever Prim's algorithm chooses an edge, that edge can replace a heavier edge in any other spanning tree without increasing the overall cost, thereby demonstrating that the greedy choice is consistent with optimal solutions. In addition to its theoretical significance, Prim's algorithm forms the basis for practical MST implementations in many standard libraries and frameworks across languages such as C++, Java, and Python, often under graph processing modules used in scientific computing, network simulation, or route optimization. Overall, Prim's algorithm is an elegant, powerful, and efficient method for constructing minimum spanning trees, combining strong theoretical foundations with broad practical utility. And its step-by-step greedy expansion from one starting point reflects the intuitive idea of steadily building a low-cost network by always choosing the cheapest possible extension at every stage.